Let's get right into it. When you see a building collapse after an earthquake, it's almost never a simple story. It's not just about the raw power of the shaking. No, it's usually something more complex. A perfect storm where a bunch of hidden weaknesses all decide to fail at the exact same time.
You've seen the images, right? In the news footage, there's always one building that's just a pile of rubble, and right next to it, another one that seems perfectly fine. It's a really haunting sight, and it makes you wonder, what's the difference? Why one and not the other? That's exactly what we're going to break down.
Well, the answer usually involves two main culprits who are basically working together. You can think of it like a conspiracy. On one hand, you've got the building itself, its design, the materials used, any hidden flaws. And on the other hand, you have the very ground it's built on, which, as we'll see, can betray a building in some pretty terrifying ways.
So first up, let's investigate culprit number one, the building's own weaknesses. What are those hidden problems in the frame that can basically doom a structure before the shaking even really starts?
You know, when we dig into why these structures fail, the reasons can be shockingly basic. We're talking about things like poor quality concrete that just crumbles under stress, or not having enough steel rebar inside to give it the strength it needs. But there are also trickier design flaws, like something called a soft story. And one of the biggest mistakes of all, designing a building as if it's floating in space, without considering how it's actually going to interact with the soil underneath it. This right here is a perfect analogy for one of the most common and deadliest flaws out there. A soft story is usually a ground floor with big, wide-open spaces. Think parking garages or storefronts, held up by just a few columns. When the ground starts to shake, all of that violent energy gets focused on those few supports. It's exactly like trying to balance on stilts during a tremor. The legs just kick out, and the whole thing comes crashing down. Okay, so that's the building. Now let's turn to our second culprit, because here's the thing. You could have a perfectly engineered building, but it can still be completely doomed if the ground it's sitting on decides to fail. When the ground itself gives way, the whole game changes. All right, I want to introduce you to a really terrifying phenomenon called soil liquefaction. Now, the name sounds kind of technical, but the idea is dangerously simple. Just imagine ground that's full of water, kind of like wet sand at the beach. If you shake that sand hard and fast enough, the water pressure builds up, it pushes the sand grains apart, and poof! The solid ground you were standing on suddenly starts to behave like a thick, heavy liquid. So here's how that happens, step by step. First, you need the right ingredients. Sandy soil that's totally saturated with water. Then you add the trigger, the intense, violent shaking from an earthquake. That shaking makes the soil particles lose contact with each other. And all of a sudden, the ground that was supporting thousands of tons of weight now has the consistency of quicksand. And listen, this isn't just some textbook theory. This is a real and devastating force of nature. The recent earthquake in Turkey was a tragic, large-scale example of just how much damage liquefaction can do. It undermined countless buildings across entire regions.
Liquefaction isn't the only way the ground can turn on you either. You can have something called lateral spreading, where the ground literally slides sideways, taking building foundations along for the ride. Or the ground can have a bearing capacity failure, which basically means it just gives up and can't hold the weight anymore. And sometimes certain types of soft soil can actually amplify the shaking, making it way more intense right where the building is.
So, we've met our two culprits, flawed buildings and failing ground. Now, let's take a look at some real-world examples to see how this destructive partnership has played out in some of history's biggest earthquakes. We're going to look at three key events that taught engineers some really critical lessons. The 1964 earthquake in Niigata, Japan, the Loma Prieta quake that hit the San Francisco area in 1989, and of course, the recent disaster in Kahramanmaraş, Turkey. This table just lays it all out crystal clear. In Niigata, you had massive liquefaction combined with foundations that weren't built for that kind of soft soil, causing entire apartment buildings to just tip over. In Loma Prieta, man-made landfill liquefied, and it took down all those classic soft-story buildings. And then in Turkey, we saw that tragic combo of widespread liquefaction and buildings made with shoddy concrete and weak reinforcement. See the pattern? It's the same story every time. Ground failure plus a structural flaw equals disaster. So, here's the crucial takeaway from all this. You simply cannot separate the building from the ground it stands on. They are part of the same system. Having a perfectly engineered structure is only half the solution. If you ignore the risks hiding in the soil, you've only solved half the problem. Okay, enough about the problem. Let's talk about the solution. How do we actually learn from all this?
How can we use engineering to build resilience and stop these collapses from happening over and over again?
The big question now isn't just how do we build stronger buildings, it's how do we build smarter? How do we design a complete system, the building and the ground together, that can actually stand up to the incredible forces of an earthquake?
Well, the answer really lies in a holistic approach. It all starts with a deep, thorough investigation of the ground itself. Then it's about choosing the right foundation for that ground, maybe deep piles that anchor into solid bedrock. Sometimes you can even improve the ground itself to prevent liquefaction. And of course, you need strict building codes. And you need to use advanced computer models to see how the building and soil are going to dance together during an earthquake.
So when engineers talk about a geotechnical investigation, it's way more than just kicking the dirt around. It's like a full forensic analysis of the ground. They drill deep boreholes to pull out soil samples. They run tests to measure the soil's strength. They analyze all that data to understand the risks, like liquefaction. And only then, after all that work, can they design a foundation that's actually safe for that specific spot. And really, it all comes down to this one powerful idea. The ground isn't just a passive platform that a building sits on. It's an active, crucial part of the entire structural system. You have to design for both, together, or you're designing to fail. So, I'll leave you with a final thought. It's a question to kind of chew on. We all think about the strength of the walls and the roof over our heads, but we almost never think about what's going on deep beneath our feet. After everything we've just talked about, it's worth asking yourself, is the building you're in right now standing on solid ground?